Hello, Mr. Erico. These are my multiple choice corrections. Well, without further ado, let's get started. Okay. On number 2 was the first one I missed on this one. It reads that all the following statements about an isolated solid charged conductor are correct except one of them. And I initially selected A, and I now realize that that is wrong. The correct answer is actually D. The electric field E just outside the conductor is directed parallel to the surface. So when an electric field comes off of a charged object, it goes out like this all the way around. So it is not parallel like a potential line. It is directly out. So that one is D, right there, not A. Number 8 was the next one that I missed, and it asked for two conducting spheres. One having twice the diameter of the other as shown above. The smaller sphere initially has a charge of Q+. When the spheres are connected by a thin wire, which of the following is true? I realize now that 1 and 2 are both going to have the same potential. So the radii differ, so their charges are going to split, but their potentials are going to stay the same when they're connected with a wire. They're going to go across evenly. So that's why it's A. They're both going to have the same potential, and not initially C, where I thought 2 would have half the potential of 1. So for that one, it was fixed. Okay, for number 12, it's a question about 2 points about the same distance. It says points R and S are each the same distance d from the two unequal charges, Q and 2 plus 2Q. As shown above, the work required to move the charge negative Q from point R to point S is what? So with potential, it's the topographical map. Okay, so you're going either up or down through that, and based on how high or low you go, that's the amount of work that you're doing. Now, these are the same distance apart, and they're in the same relation to each other. So they're staying on the same level of that equipotential surface. So they're not going to do any work on themselves. So the answer is D, D and not C. It's not going to do any work because it's not changing in elevation. It's just going to stay the same. So that's why it's D. 13. 13 I was going to talk to you about in person. So we'll deal with that when we get to it. Number 14, it asks for concentric conducting spheres of a radii A and 2A bear equal but opposite charges, plus Q and negative Q, respectively. Which of the following graphs best represents the potential for V? The potential V as a function of R. So I initially looked at it like this, with it gaining exponentially as it got to the edge, but I realize now that the potential on a conducting sphere is going to be constant until you reach the surface, and then it's going to exponentially decay like that. That's just how the relationship works with potential and conducting spheres. So I realize the answer D, not C, but D. Anyway, the next one I missed, number 15. A positive charge of 3 times 10 to the negative 8th coulomb is placed in an upward directed form uniform electric field of 4 times 10 to the 4th newtons per coulomb. When the charge is moved 0.5 meters upward, the work done by the electric force on the charge is what? So when you look at that one, you have to break it into work equals F dot D. And what does F equal? F equals QE. So you can plug in your Q, your coulomb, 3 times 10 to the negative 8th, and your electric field, which is 4 times 10 to the 4th, right here, and then you plug in your meters right here, and you end up, when you plug that in, you get 6 times 10 to the negative 4th. This one right here. So, and that's the work done. It's asking for work. Work equals F dot D. And so that's the answer. So 17. 17, next page. So this one is dealing with flux. and flux equals Q enclosed over epsilon naught. Now, flux is all about the electric field going in and coming out of an object. Now, normally when you're dealing with flux and you use this equation of Q enclosed over epsilon naught, you're talking about the whole object. In this question, it's asking for what is the flux through one face, one single face of it. So what you have to do, a tetrahedron has 4 sides, and it's only asking for one of them. So you have to divide it by 4 to realize what's going to be out of the single surface. So that's why it's D, or sorry, that's why it's C, and not B. For 19, this one's been intuitive. If it is a negatively charged, it's asking for a circular ring, they put an electron in the middle, where does it go? If it's a circular ring, and these are negative, and these are positive, the negatives are going to move away from each other, they're going to want to repel, and the positives are going to want to attract it. So obviously the net force is going to go down, which is to the bottom of the page, just like it says on option B over here. Option B. So it's not going to go into the page, but it's going to just go down to the bottom. For 21, it's asking for what is the radial component of the electric field associated with potential with the function a r to the negative 2, where a is a constant. So V, your voltage, your potential equals the negative integral of E in relation to R. And so what that means is the derivative of V versus R, not T, R, is going to equal negative E, negative electric field. So knowing that, let's take it to what the example was given. V equals A R to the negative 2. Okay, so take the derivative of that, and you're going to get dV dr equals negative 2a r to the negative 3. But remember that it's not just the derivative, it's the negative derivative, because you have this negative sign here. So you're still going to need to put another negative there, and 2 negatives make a positive. So E is going to be 2ar to the negative 3, but it's going to be a positive 2ar. It's not going to be a negative one, which is something I missed on the test. It's going to be positive because there's an extra negative. For 22, that was another one that I was going to talk to you about in person. And so that 23 is also actually the last one that I have on part 1. In the box one, it says the point charge Q as shown above is at the center of the metal box that is isolated, ungrounded, and uncharged, which the following is true. So the net charge on the outside surface of the box is Q. That's what's going to be true. Just like with a sphere, if I'm not mistaken, it's going to be Q, and then on the inside of that surface, negative Q, and then the outside is going to be positive Q. This box is uncharged, so it has no charge already. It's just going to take the charge of what this is. And so on the outside, it's going to match it because it's an enclosed surface. So it'll be Q, and on the inside of that square, or that cube, it's going to be negative Q, and on the outside, to match that, it's going to be positive Q. So that's why A is correct. 24, these two spheres are uncharged. They have no charge at all. And so when they're touched by a negatively charged rod, if it's only coming into contact with a negatively charged particles, and it has no other charge, it's obviously going to be negatively charged. There's nothing else touching it. So that's why it's a negatively charged spheres. So on to part 2, and I only missed 3 on this one. So on number 2, on the next part. The question is dealing with two negative q's that get added a positive q in the middle. And so initially your force is going to be force equals kq squared over L. Okay, so that means your q is FL over kq. That's just what it's going to equal, and that's going to come back later in the equation. So F over 2 is going to equal 2kq over L, because L over 2, bringing the 2 back up here, that's where you get the 2 right there. And then plus the second one, because there's 2 right here, 2kqq over L. And again, that 2 is up there because L over Q would come up to the top. Anyway, when you add those together, you get 4kqq over L. Now, plug that right where the F over 2 is, and if you solve for Q, you get FL over 8kq. Now take away the 1/8 to make it relational to your initial equation, and you get 1/8 of the initial problem. So that's what it's going to 1/8 of Q. So that's why it's going to be D and not C. You have to add these two together and then make it in relation to the first variable that you found up here. The next one I missed was 8. 8 was a question about potential, I believe, or no, electric field. So this one is having to deal with the electric field, which on a graph like this is the slope. When is the electric field going to be 0? Now, right here, this -2 is obviously a lesser magnitude, a lesser absolute value, than a +3. So this mountain graph, is what I like to call it, this potential graph, is going to be greater, okay, than this one. So it's never going to fully get to a 0 slope over here, at least not in these regions defined here, because it's just too large. The only time that it's going to get to a 0 slope is over here, because there's a lesser magnitude. It's 2. It's not as great, so it's going to be easier for it to not only cross this axis to make the electric potential 0 at one point, but also the electric field is going to be 0 as well. And then the last one, number 10, this is simply a graph of electric field versus voltage, or sorry, electric field versus distance. Okay, so it's asking for the magnitude of the electric field. So it's not even really, it's not trying to trick you. The closer you get to a charge like that, the greater the magnitude of the electric field is going to be. So it's intuitive that these two are going to be the greatest right there. It's not going to be any of these other graphs. The electric field is going to be greatest closest to the two charges, and that's exactly what we see in graph A. So those are my corrections, and then I'll talk to about the ones that I had some more trouble with you in person. But anyway, all right. Have a good spring break.